Okie dokie. So I want to talk a little bit about kinetic friction force and the coefficients before you get too far into this. So just a little note on that, because this was a little quick in the pre-lecture video, so I just want to kind of clarify a couple things. You'll notice that there were two types of friction that were mentioned. One has a little k, one has a little s. The k stands for kinetic, meaning that's the friction that's involved when you have an object moving already. So this is our kinetic piece. And S is for static, meaning it's still stuck in place, okay? And there's kind of two things that affect friction, but I want to first talk about this static thing. So static friction is going to kind of hold something in place until it eventually starts to move.
You have to, oh, there, it's fine.
It's all good. You can Photoshop yourself out later.
Yeah, no problem.
I'm just kidding, you don't have to do that. All right, so if I hold my eraser on the papers and if I gradually move this upward, see how the eraser started to slide down right about there? Yeah. So it eventually reaches an angle where it's not moving, not moving, not moving, and then eventually starts to move once I reach a certain angle. So what I'm doing there is I'm switching from static friction, kind of holding the eraser in place, not allowing it to slide down, from when it absolutely can't hold it anymore, and then the object starts to slide, so it turns into kinetic friction. So the big idea with both of these, what you've seen here, it's going to oppose or prevent motion. So it doesn't cause motion to take place. You'll never have friction like jump out of a table and push something backwards. It doesn't work that way, okay? So again, we're either opposing the motion, kind of slowing it down, not allowing it to go as fast, unless it's at a constant speed. And then, or we can prevent motion altogether, keep it from sliding. Okay, so there's lots of places where we like static friction. Okay, if you want your car to be parked on an icy hill in the wintertime, you want lots of static friction there, so your car doesn't slide down the hill. Okay, so a couple things that contribute to this. Kinetic friction is related to two things. Mu times n, which you saw this in the video. Mu is your coefficient of kinetic friction, meaning what is the roughness of the material that's there, okay? And then also it has to do with the normal force. So what's the pressing between the two objects that have the friction between them? Static friction does not have a locked-in value, okay? Static friction can range. It's going to be less than or equal to the static coefficient of friction times the normal force. So kind of what these guys are, that comes from the material. So you're usually either given that number in the very beginning, or it's something that you do, like with this problem, you're given everything else and it's something you solve for at the end. Usually these numbers are anywhere from 0 to 1, so they're very small decimal numbers. If it's something that's like 0.9 or 0.8, maybe you've got like a concrete or a carpet, something really rough that doesn't allow things to slide easily. If it's closer to 0, maybe it's an icy surface or something like a tile that doesn't have as much friction associated with it. So it's just kind of a relative roughness of the material that's there based on the two surfaces that are sliding across one another. And then your normal force will also affect things, so I want you to try something really quick. Take your two hands and rub them together. If you feel a little bit of heat, okay? Now I want you to try something a little different. It's going to look a little bit goofy, but I want you to take and do the same thing, but I want you to squeeze your hands really tight between your knees and do the same thing. It gets a little bit warmer, right? It gets significantly warmer, almost, it's very noticeable right away. So the normal force is really going to affect this friction as well. How much are the surfaces pressed against each other is going to factor in the friction. The more you press against each other, the more friction, the harder it is to move your hands. The less you press, the easier it is, okay? So when you have something like a box sitting on the ground, if it's really, really heavy, then you're gonna have this huge normal force going up. But if it's a very lightweight object, then maybe it's only a little normal force. Okay, so the normal force that's there will have a factor on, but between the two surfaces, I should say, that's going to have a factor on this friction thing. All right, so just a little note on that before you continue this problem. So take another couple minutes, see if you can get this thing finished up. Make sure you're using your problem-solving process, and then I'll go over it. Okay. Alrighty, so going over this question. Alrighty, so we've got our box being pulled up. Oops, gotta get my chalk. Alright, so we've got our diagram. What do we do next?
Label it?
Yep, we could label it. So we've got our box. This is just because the first step is just kind of drawing a picture of the setup. So we've got a box, we've got something pulling on it. There's no people in the story. There's nothing really else that's going on. So this is just kind of a story. What's step 2? Freebody diagram. Okay, so I'm going to use, you can either use a little dot or a little block. Doesn't matter to me, just as long as it's a small dot-like object or dot-like symbol. Okay, we've got to get all of the forces that are acting on this. So I'm going to go ahead and write the obvious one first. It's already in our picture. And again, all the arrows point away from the spec. So I'm going to put this here, label it as 500 newtons, and then just for clarity, I'm going to go ahead and write the 30-degree angle in there. Okay. So to check all my other contact forces, anything else that's there, I can see in my diagram that there's a surface underneath here. So that surface is going to push perpendicular to its orientation. So I'll call that the normal force. I know that the object has mass, so it's going to have weight going down. So I'm going to draw an mg. And then I have to figure out if there's anything else that I need to include in my diagram. Any other forces that are acting on our block? Friction, yeah, that's that kind of invisible force that's kind of pushing backwards that you can't technically see when you draw it. Okay, so I'll draw that opposing motion. And is this going to be kinetic or static friction? Kinetic, yeah, because it says it's accelerating. So we know we've got motion. So you just call that kinetic friction. Okay, so that's our diagram. Next part, step 3, choosing a coordinate axis. So the purpose of step 3 is not just to pick any axis, but it's to kind of make a smart choice on where you want your positive x direction to be. Typically, you put your positive x direction with acceleration. Okay, so in our diagram here, if we look at our object, overall, which is the direction of our acceleration going to be? It's probably going to go straight to the right. The box is not going to float upwards or go down into the ground. It's not going to suddenly turn around and go the other way. Okay, so I'm going to just do like a little side note up here that I'm going to call to the right positive A. So what that does is this makes this direction your positive x. So then opposite's negative x. And then perpendicular to that is your y's. Okay, I'm just drawing those kind of off to the side so they don't get mixed in with my diagram. So it's basically like a normal xy axis in this problem because of the way that it's oriented. Okay. All right, now I can do Newton's laws. Step 4. This is the big part. Newton's second law, which I used to have it written up there. The sum of all of our vector forces is going to be equal to the mass times the acceleration of the object. And those, again, these are both vectors, so there's directions tied to this. So this is where we have to think about how all of these forces are working together, because this is a sum sign. Means you got to get some sort of a total, but you can't just simply add all of these numbers together. Okay, we can't just put them all in the same basket. We've got to think about which direction they're going in terms of vectors. So for the x direction, so that's one of our axes, and then the y direction for the other one. Okay. All right, so I want to look at everything going positive right. This one's at a diagonal. So we know from our pre-lecture video, you've got to use the component, okay? Just the stuff that's straight to the right in that positive x direction. So we'll say 500 cosine 30. And again, that's just to draw that out. That'd be this x component. And then there'd be a y component to go with it. Then anything else pointing to the right? No. Anything pointing to the left? Yes, we got friction. So opposite direction, opposite sign. And again, we've added up all of our forces, and then it's equal to mass times acceleration in the x direction. Okay. Alrighty. Questions on that? Anything at all? All right, then the y direction, the up and down stuff. Okay, so we've got the normal force going up. I'm going to say up is positive and down is negative. We tend to like that pattern. So normal force up. The 500 is also kind of being pulled upward from the object. So it's kind of contributing to that upward net force in the y direction. So I'll say plus 500 sine 30. That's opposite. Nothing else up. We know gravity's pushing straight down, minus mg. And then, again, sum of our vector forces is the mass times acceleration in that direction. So this will be MAY over here. Now what's the acceleration of the box in the upwards and or downwards direction? Zero. It's not being lifted off the ground. It's not moving through the ground. So this MAY over here, we can just say that is zero, just for simplicity. All right. Now at this point, we know all of our numbers for a couple of these places, but this is where you go to that next step and look for if you need any of those little intermediate equations. So this is an example of a small intermediate equation you can plug in, and then you can, if you know everything at that point, then you can go ahead and solve. So if I look at what I'm actually solving for here, part A asks for the kinetic friction force. So if I look at my things that I did in step 4, I'm going to try to find that variable and see if it's here. So kinetic force of friction, right there. So do I have enough information to solve for it, or do I need more stuff? What do you think? We can solve for it, right? We know mass. The acceleration is given to us as 2. Okay, so you've got, you can go ahead and solve. So this will be 500 cosine 30 minus Fk equals, what was the mass? 50. Yes, so make sure you don't get confused with the mass versus weight. So we'd have 50 times 2, or 100. This thing turns out to be something like 433. Do a little bit of algebra and you end up getting that your kinetic friction force is about 333 newtons. Okay. Questions on that? Any questions at all on that? Okay, so then part B, solving for the coefficient of kinetic friction. Well, I know that I don't see coefficient here anywhere. The mu variable is missing, that little Greek letter. So I need this guy. So I know what I just solved for was this 333 Newton friction force. So I can kind of start here, pick up where I left off. Fk is mu times the normal force. Uk, I should say, excuse me. This is 333. And then what is our normal force? Is that something that I know? Can we solve for it? We can solve for it, right? We've got two equations up here. That's why it's important to write both. Usually you need the other one at some point in the problem. So you know the mass, you know gravity, you know 500 sine 30 is just a number, so you can get your normal force from there. Those of you that did this, what did you guys get for your normal force? 240-ish? Okay, so we'll say 240-ish. It's totally fine for that, looks right. Alrighty. And then the coefficient, I think this turns out to be something like 1.4. So two things. One, with physics we've got units behind numbers. So what is my unit of our coefficient of kinetic friction? Yeah, there's no units. If you look at what you did to solve for this, you did 333 divided by 240. So you did frictional force in newtons, and you divided by normal force, another measurement in newtons. So these guys cancel. So this is it. That's all you need. 1.4 is a unitless number. Now I will say that when I wrote this problem, I didn't solve it probably ahead of time, so this is kind of an unrealistic number. It's not impossible to have a coefficient of friction greater than 1. It just means it's super, super rough. But again, you're probably going to see numbers that are smaller than 1, something like 0.5 or 0.7 in the future. So just kind of keep that in mind. Yes?
Can you go through the equation? I didn't get 240.
Okie dokie. So for Fy, we've got normal force plus 500 sine 30 minus 50 times 9.8 equals 0. And let me grab my calculator real quick. Some of these numbers I don't like to do in my head.
Does gravity have to be negative or just 9.8?
It's just 9.8. So that's a good question. So is G negative here? Okay. So G is just the acceleration due to gravity. We assign the direction based on what we know about the story. Okay, so for example, when you did your kinematics questions, if you had an object thrown upwards, you probably made 9.8 negative because that's going against that motion. We sort of already did that up here. Because again, the thing that's making mg a vector is gravity. The mass is not a vector. So we've already accounted for the fact that gravity is down in our net force equation. So make sure to not double account for the same thing, so it'll make your force the opposite of what it needs to be. Okay. Did that fix it by any chance?
Yeah.
Perfect. So yeah, so then if you subtract around 50 times 10, around 500, that should work. All right. Other questions on this one? All right. Next question. All right, so this next question. A large truck pulls a trailer. Consider the force of the truck on the trailer and the force of the trailer on the truck. How are the forces and accelerations related? So you're trying to find, and you're choosing two answers here, one for the force options and one for the acceleration options.
Oh, okay.
All right, it looks like everyone has their answer in for this. So let's go ahead and see what you said. Ooh, all over the board here. All right. I'm going to draw a little picture of this just to help with it. All right. So we've got our truck and pulling a trailer. Okay, I'm not going to do a semi-truck with a trailer because I wanted there to be two clear objects, just for the picture's purposes. Okay, all right, let's say that they're moving this way. Okay, so acceleration, remember, acceleration's just a change in your velocity. How much does your speed change and in which direction does that happen? So let's say that the truck starts, let's say it's at a stoplight right now. So it's sitting in a stoplight, okay, so its velocity is 0, and then the stoplight turns green. And then let's say over here that the truck is moving, I don't know, 10 miles per hour. right at this point. How fast do you think the trailer is moving at this same point? Same, different? It's the same, right? How is it that they can be the same speed? And be careful not to overthink this one. This is not technically a physics question. Go ahead.
Since they're connected, they'd be moving at the same speed.
There you go. Easy as that. No, we don't even really need to think about physics here. We know that these guys are stuck together. So if the truck moves that way, the trailer's gonna go right along with it. If the truck backs up, the trailer backs up right along with it. So they stay together as a system. Okay? So this is going to have a one system mass, this whole thing that accelerates back and forth. Okay, so what does that tell us? D, E, or F? Which one of these is true? E, yep. E for elephant. The accelerations are equal. Alrighty. Now for the other one, the force on between the two, if we measure the force pulling that way versus measuring the force pulling this way, what do we know about those pairs right there? How will they compare to each other? What was Newton's third law of motion, remind me? Every action. There you go. Alrighty. So this force, because we didn't ask for the total force, I didn't ask for friction or anything else. What I asked for is this relationship right here. So if the truck is pulling on the trailer with some sort of a toe tension, whatever that is, then that trailer is going to be resisting that toe. And the equal in magnitude and opposite in direction. So for our forces here, the magnitudes are equal. So B is also true. Okay, so be careful with these types of problems when you have two objects because it's asking for a very specific force here, not an overall net force. Okay, so let me mark the correct answers here. So we've got B and E. All right, so keeping that in mind, go ahead and do a little math problem with this one. All right, I'm gonna go ahead and start talking about this one. I'm seeing a lot of these two numbers as I walk around the room. Did anyone get anything else? I just kind of took, go ahead. 700 newtons, okay. I know what you guys are doing to get these numbers. We're gonna figure out which one of them actually answers this question. They're all kind of involved in the story, but not all of these numbers actually answer this question. All right, so doing our problem solving process, I drew a little picture out just so we were kind of all on assigning things in the same direction together as a group. But if you had your stuff moving to the left, that's okay too. So I've got a car and a trailer, and I'm gonna say that they're moving and accelerating that way. And that's, we know the acceleration's 1.4. So that's the acceleration of our system, both of them working together, okay? Alrighty, free body diagram. I've got two objects, so I'm gonna do two free body diagrams. Need one for each object. So the trailer, if I isolate the trailer, I know that the ground's pushing the trailer up. I know that it has weight. Okay. I see attachment here, it's attached to the car. So I'll just call that, this is where this labeling is kind of helpful. The force of the car on the trailer. So the force of the car physically pulling on the trailer. I'll call it C on T. Okay. All right. Now I had a lot of people kicking around the idea of friction here. Okay. Now if we think about how these guys actually move, these frictional forces here, this coefficient and the normal force relationship is when you have two things that are kind of sliding past one another. So you want to ask yourself, are these objects that are moving sliding along the ground? What do you think? They're not really sliding. Now, if it slammed on its brakes and then the tires kind of stop turning and then it slides, then you might have some friction. But as these rotate, if you have your tires spinning, all it's really doing is gripping onto the road and moving gradually that way. So friction here is not really going backwards like it would with a typical object moving to the right or to the left like we have done in our previous problems, okay? And in fact, if you have a really, really long hallway that's nice and flat, so no changes in the ground at all, or no changes in the normal force, so to speak. And if you roll like a bowling ball, like a nice rigid rolling object, if you roll it down the hallway, it's gonna keep going and going and going and going, and it's not gonna stop. The reason why, if you roll an object, it starts to slow down is because there's little kind of sort of invisible divots in the ground that's kind of changing, so maybe it's pushing just a little bit on the tire right there. Okay, so what's really happening to get these things moving is we need something to kind of generate that tire rolling to happen. What makes your tires roll? Yeah, your engine. So you do something with your car to get the car moving, okay? So we don't really have, so the point is here, we don't have a backwards kinetic friction force in this problem, okay? So that is it for the trailer's diagram. Now, just to be clear, this is for the trailer. Now we'll do one for the car. Okay. So we just talked about this. The car is going to need to get these guys moving. So I'll have an engine force here. The trailer's attached to it, so it's pushing backwards. I'll call it F of trailer on car. And then it has its normal force and weight. Okay. All right. So in this question, I am asked for the force of the car on the trailer. This is how you have to be really careful about which one of these you're reporting your answer for. Okay. So I need this force, which is essentially this force too. Okay. Now, I'm not given engine force. It doesn't say in the problem that the engine is providing some amount of newtons of force, so I don't know what this is. So I'm going to try to see if I can solve this over here. Less unknowns, okay? Alrighty, Newton's laws of motion tells me the sum of my x direction forces, which is this one, is equal to the mass. So this is the trailer we're being asked about. So I'm going to use the mass of the trailer times the acceleration of the trailer. And the mass of the trailer, I don't remember what it was, 500 kilograms times the acceleration. They have the same acceleration, 1.4. Alrighty, 500 times 1.4, 700. Yes?
Why is it, so it's the force of the car on the trailer, but why are we taking the mass of the trailer?
Force of the car on the what?
Trailer.
On the trailer. So the on the tells you what your object is that you're being asked about. So it's your the free body diagram you drew. We're being asked about what's happening to the trailer, not the car. So yes, the car's providing this force, but the car's mass is not responsible for providing that force. The car's engine and its components are responsible for that force. Okay? So the on the is really important in this sentence. It tells you which object you're being asked about. Think about it as force on the object. Then that object is what your diagram you're using. All right. Questions on that? All right, similar follow-up question here. Same story, but now I'd like to know what the net force is that the engine needs to provide. So what is our engine force? A tie here between none of the above and C, which is 400. All right. I'm going to do the usual. I'm going to do my problem-solving process, okay? So I've got a box on the floor, so I'm going to draw a picture of it. And Alex is pushing on it. I'm going to have him push this way. He's pushing on the box, okay? So if I draw my Freebody diagram, I know that it's pushing this way. Okay. It means it says he's unsuccessfully pushing. So unsuccessfully, what would that look like if he's unsuccessfully pushing the box? Yeah, he can't. He's not moving it yet. He needs a little more oomph. Okay. So something's fighting against him. What's fighting against him? That's the friction. That's what we're being asked about. Okay. All right. So static friction, and I'm sure you guys did the N and M machine. Okay. Any other forces? All right. So coordinate axis is kind of obvious. We can use the normal X and Y thing. So if I write out Newton's laws of motion, X direction I get push minus friction. Y direction I get N minus mg. Then on the other side here, these are always mass times accelerations in that direction. So what goes here on this one if he's unsuccessfully pushing the box? So both these are 0. This one's 0 because it's at rest. Okay. This one's 0 because it's not gonna float away from the floor or sink down into the ground. So kind of two different reasons for these zeros. Okay. All right. So if I think about this, my push force, I know that number. That's something I know. That's 300. I'm gonna give you guys a second chance on this one. I'm gonna close this one. We'll say all these are right for now. Okay. All right. Let's see if we can get a bigger majority. If anyone changed their mind. So the static friction underneath the box. Much better. So what we've seen here, let's look at these two options here. Some still say C. That was a large majority before. Now we've kind of flip-flopped our choice, right? Now I know how you got C. How'd you get that number mathematically? What did you do? You did mu times the normal force. But what you said there, that there's something about this equation. You turn this into an equal sign. Okay? So that equal sign is only true if you are at the absolute maximum static friction that you can exist at. Okay? So what this number tells you, what 400 is how much force he needs to exceed to get this thing moving. So in other words, if he pushed with 401 newtons of force, this thing would start to accelerate to the right. So he's got to exceed that number. So if we made this 400, which is what that majority was, if we made this 400, let me see what that's going to look like here. That doesn't work, does it? Okay. This would mean that if this thing was larger, that little friction fairies would come out of the ground and move the object backwards. Doesn't work that way. Friction's not going to cause the object to go the other direction. It's just going to stop the motion. So this is going to be 300. Alrighty. So in this problem, Fs max is the 400 newtons, but not the answer to our question. That make sense? Any questions on that? All right, on to our next one. So your notes from the pre-lecture video will be helpful for this. All right, an object is at rest on an inclined plane. What is the direction of the friction force? I want this to kind of be a little quicker question.
Preliminary exam.
So, it's at rest, it's not moving, okay? If there was no friction, if this hill was really, really slippery, what would happen to the box? It's going to slide down the hill, okay? So our direction of potential motion is going to be this way, okay? It's highly unlikely, unless we push it up the incline, it's not going to go that way naturally on its own, okay? Now what's causing it to want to slide down? Yeah, part of gravity, and I showed that that gravity coefficient, or excuse me, gravity component triangle in the pre-lecture. So if this is not moving, then we need something going against that potential motion. So I'm breaking chalk today. So your static friction force is straight up along the incline, so that would be E. Questions on that? All right, slightly different phrasing. I'm going to change this up a little bit. Make that one true. Same sort of story. The object is now kicked along the plane upwards. What is the direction? It's going to be down along the incline. So with this one, if we kick the object at the bottom, so we give it some reason to go moving upwards. So now our motion of the object is going up along the incline. And again, if there's friction there, it's going to oppose that motion. So your friction in this case, now I'm going to write kinetic friction because now we're moving, we're actively moving. So it's going to be kinetic friction, unlike the last problem. All right. Now let me ask you this. So we've got friction going this way. Our velocity's going up. We can leave the same choices here, but I want to ask you a different question. So same choices, different question. What's the direction of acceleration? Net acceleration. So if we set net force equal to mass times acceleration, which way would our answer end up being? One. All right. Good, good, good. All right. So, if we kick the object upwards, okay? So I give it a shove when it's down here. What eventually happens to the object if it's moving this way? It's going to slow down. There's friction there. So eventually it's going to reach some maximum height. It's going to go really quickly, and then it'll eventually slow down to get to the top. Okay? So in other words, we go from, in the beginning of the story, from having velocity, we give it a kick. We don't actively push it the whole time. Okay, so we just kick it straight up. So we go from having velocity to having no velocity. Okay? So to fight against that velocity, to decrease it down to 0, we need acceleration to be acting in the opposite direction. So your net acceleration for the object, even though it's moving up the incline, your net acceleration is opposite. It's going to slow down that motion. In the next question, you'll be able to write out your Newton's laws to kind of verify this direction. Okay, so I'm going to turn on that one at this time. So we have this story given to us. We're told that we give a block a kick, an initial velocity of 5 meters per second, and then we want to know how far it goes before it comes to a stop up here. Okay, so if I want to relate the final velocity, the initial velocity, and the displacement, whatever the x value is, we can say that xi is 0, and we can say the final x is what we're looking for. So we're trying to find that final position. Okay. Now there's no equation that just relates 3 of these things. We really need either time or acceleration if we want to talk about how those guys are related. So that's where you want to think about which one of these is kind of easier to figure out. So it doesn't tell me how long this takes. No time is given. And there's really no other way you can figure out what time is unless you're given it or if you already know the acceleration. So we really need to figure out what acceleration is before we can answer this question. Okay? Well, based on what we've been doing so far, where are we going to get that acceleration from? Where do we get that from?
The y-axis gravity.
Yeah, we need some forced stuff. Okay? So the connection between chapter 2, which was kinematics, so you had BF, BI, your X's, your A and your T. The connection between chapter 2 and chapter 4 is the fact that chapter 4 has your Newton's laws of motion. So both these chapters are connected that way, but with acceleration. Okay. So your acceleration ultimately is going to be causing this thing to slow down, so we have to use forces to figure out what that acceleration is. If you did not watch the pre-lecture video, make sure you do so, otherwise this next piece is going to be pretty confusing. So for my forces, I've got to draw all the forces, normal problem solving process, all the forces on the diagram. I know that it's got gravity pushing straight down. Okay. I know that the inclined plane is pushing straight out, perpendicular to the inclined plane. I drew a little dotted line here just so my arrows were all pointed in the right direction. Okay. So this is where we have to say, are there any other forces? I've got the obvious one, the ground and gravity. Those are usually always there. So now I've got to look for other things. Friction one way or the other? Nope, just says the problem's frictionless, so I don't need friction. Any other forces? Anything other attached to the object, pushing the object, pulling the object? Anything else? So this is where you're asking yourself, is there something actively pushing this box up the incline? No, there is not. It kicks it, and that's it. One time, one kick, boom, and then you're done. And then it goes up the incline, and it starts to stop. Okay? Well, we've got to figure out what's stopping this object. Why does the object not go on forever? What's pushing against that? Gravity. Some of it. Okay? So gravity, again, has 2 responsibilities here. This is where you need your component triangle. So gravity is, 1, it's going to keep it attached to the surface of the incline. It doesn't, like, bounce along the hill. So that's going to be this component here, which we'll call, if this is our theta, which we know is the same as 20 degrees. Okay. This is going to be mg cosine theta. And then to finish out this right triangle here, you can see, finish out that right triangle here, there's going to be an opposite side, and that's your mg sine theta. Okay. So from the video, I showed this in great detail. So what we really have here, using that tilted axis, I'm going to turn it sideways. Usually we have an XY axis like this. That doesn't help me here because the object's not moving in this direction. It's not moving in that direction. So I'm going to tilt it to where my potential acceleration is in line with the inclined plane. So positive x is here, negative x, positive y, negative y. Just like in our video. Okie dokie. So x forces, y forces. Okay, so I'm going to start with the y direction. It's a little more obvious. So the normal force is out of the inclined plane. Fighting against that or opposite in that direction. Anything pushing into the incline, which is part of gravity. Gravity has two roles. Pushes things into the incline, also wants to push it down the incline, down the hill. So we've got n minus mg cosine theta. We'll deal with the other side in a second. X direction. We've already talked about the fact there's nothing pushing the box along the incline. But we do know that gravity is what's going to be pushing it this way. That's that down the inclined direction. If we said that this is positive, gravity's negative. Okay. With that hint, take another few minutes and continue to solve this. Then I'll go over it right before we end. So in the x direction, we need to fill in the other side of the equal sign. That's where we're trying to put in our mass times accelerations or zeros. So we've got in the x direction, that's along the incline. That's where your acceleration is tied to. From the previous question, we answered that. We put m times a there. I recognize that the box is not moving in the y direction. It's not going away from the hill. It's not going into the hill. So this is 0. And if I look at this, okay, mg sine theta equals ma. Do we need the mass? Not needed, it cancels. Okay. So this tells you that negative g sine theta is the acceleration of our object. So then when you start to do that kinematic stuff, I would probably choose this equation. Because it relates all of those things that we already wrote down. We have to stop the object. We started it, we kicked it with a velocity of 5. We found with forces that its acceleration is a negative thing. So negative g sine theta times delta x. And then you can solve it from here. Questions on this? Make sure you do not plug in negative 9.8 here. We already did that using Newton's laws. All right? Have a good one. I'll see you on Thursday.